So, I hope that there is somebody who is listening to me. And I would like to start with numbering. I'll use different numbering, different from lecture notes. So chapters are the same, but lectures are real lectures. Hence, so today's second lecture, so everything from today will be with first number 2, lecture 2. Then first section for today is about upper and lower bounds. Upper and lower bounds. Okay, we'll start with definition. A set is called bounded above if there is a number let's say y such that for all x in M, x less or equal than y. Such a number y is called an upper bound. Analogously, we define boundedness below. So, I said M is called bounded below if there is a number y such that for all x in M, x greater or equal than y. Such a number y is called a lower bound. So, if we use real line and let me denote points in our set M. So this is M, our set M. So an upper bound, for instance, this is an upper bound y. The set is bounded above. Analogously, it's bounded below if we put a number y which is less or equal than any number of in the set M. And what is more important is the notion of the least upper bound. So next definition. The least upper bound for M is the minimal upper bound. Of course, there is a question if such a number exists. It's another story. But at the moment, this is a definition of something which maybe not exist. So equivalently, we may characterize it in a different way. So what is minimal? Maybe I'll write it even here, i.e. for any so let me introduce the notation. The least upper bound is denoted the least upper bound for M is denoted by sup M. Sup M. So for any upper bound Y for M, Y greater or equal than this supreme. So this is indeed the minimal. So what is meaning of words the minimal upper bound? So sup is abbreviation of supremum, Latin word supremum. Analogously, we may define the greatest lower bound for M, which is denoted as inf M, is the maximal lower bound for M, right? So again, infimum is abbreviation for inf is abbreviation for infimum. And let us look at examples. So consider, for example, M is interval infinite semi-axis from 1 to infinity. So here, no upper bounds at all. There is no upper bound, no such a number y such that for all x less than or equal less or equal to y. But any y which is less or equal than y, less or equal than 1, is a lower bound. So it means that supremum doesn't exist, and infimum is equal to 1. Another example is interval from 0 to 1, including to 1, not including 0. Here, upper bounds every y greater or equal than 1. Hence, the least upper bound, supremum, is equal to 1. This is maximal element of M. And lower bounds are numbers y such that y less or equal to 0. Hence, infimum, the greatest lower bound of M, is 0. So in this case, 1 belongs to M, but 0 doesn't belong to M. Okay, and it turns out that the existence of the least upper bound and the greatest lower bound is a result which can be taken as an axiom, in fact. It's equivalent to the completeness axiom. So let me formulate this version of completeness axiom. Let's say A12 prime. So version of completeness axiom. Any non-empty bounded any non-empty set M bounded above has the least upper bound. Before to discuss this assertion, or possibly an axiom, we should note, so this may be written as a remark, supremum and infimum of a set, if exist, are unique. So it easily follows that, you see, every least upper bound is automatically upper bound, hence if y1 is supremum and y2 is supremum, then by the property that y is the minimal, we have both inequalities y1 less or equal than y2 and y2 less or equal than 1, 1. Hence, y1 equals to y2. So they are the same. So now let's start to discuss this assertion. Better to say, what we want to prove is some kind of theorem, in fact, right? This is an assertion. So A12 and A12 prime are equivalent. I don't want to use the word theorem here, because this is some kind of discussion of possible axioms. So we want to discuss a possibility to change one axiom, to replace one axiom by another assertion. And in fact, it is possible to replace each of them by other assertions. And sometimes it is made in a different way. But we will not discuss other possibilities, so only one possibility will be discussed here. So, since we discuss the equivalence of two assertions, we have to prove two assertions. So, firstly, A12 implies A12 prime, first part. So, we suppose that A12 is valid. Completeness axiom as it was given in the first lecture. Okay, now we have to prove A12 prime. So let M be a non-empty set which is bounded above. So it means that there are upper bounds. So bounded above means there are upper bounds. And we denote B by definition is the set the set of all upper bounds. Okay, so like this. Now we put A by definition contains all other numbers. So the set of real numbers without the set B. we need to check that A and B satisfy all suppositions of A12. Of course, by definition, second supposition, namely the union of A and B equals to R, is obvious. This is just as we defined those sets. So, hence, what we need to check before to apply completeness axiom is that for every x from A and y from B, x less or equal than y. That is what we need to check. So, if x and y, so better to say we need to check this one, right? Okay, we'll prove by contradiction. By contradiction. Suppose there is a pair, there are x and y in the set A, x in the set A, y in the set B, such that opposite inequality is true. X greater than y. So, y is an upper bound for M and it means that for all, let's say A in M, A less or equal than y, and x greater than y, hence those two inequalities together imply A less than x. Hence, x is an upper bound for M, and that is a contradiction. So, x belongs to B, and we supposed x belongs to A, its complement. So, all suppositions of completeness of the completeness axiom are satisfied. Hence, by A12, there exists psi. Oh, it seems it's the first time when I use it, but let me avoid it for a while. There exists psi or xi maybe such that for all in fact, there are two possible conclusions which are equivalent, so maybe like it is in your lecture notes. There exists psi such that if x less than psi, then x is an A, and if y greater than xi, then y is in B. That is the conclusion of A12. Now, we may check that in fact, so this is a claim, claim psi is supremum of M. Oof. Why is the class here? All of us are in 115 kpm. But we are. Вы видите сообщение? Спрашивает, почему класс здесь. Все мы 115 кпм. Ну, мы же 115 кпм. I don't understand this question. Why is the class here? All of us are in 115 kpm. This is 115 kpm. What is the question then? Strange. We have a break. Right? Not yet, not yet. Okay. There is another link on the website. О. На сайте МФТИ в 115 аудитории нет трансляции. То есть мы не можем трансляцию сделать? Я что-то не пойму. Ну вот Мария Каплина, это значит с международного отдела, она тоже говорит, что с сайта МФТИ видео не переходит на YouTube. Я не знаю, куда трансляция идет. Она послала ссылку в другом чате в YouTube. Ошибка в ссылке была. Okay. So it seems that many were not able to listen from the beginning. What can I say? But there is a, I mean, you can find the lecture later if, but I erased something. Yeah, so in any case, it's pity what I can say. I am sorry for this misunderstanding. I don't know what happened, why it happened. Yeah, so somebody agreed with me that you can watch the replay. Of course, the translation is essentially better because you may ask me something during the lecture. That is always better than listening the replay. But what can I do? Okay. It's a time for break, but I think... Ничего, мы уже потеряли уже 5 минут, да, из-за моего опоздания. Без перерыва, ничего же. Я имею в виду вам лично. Okay, so let's continue without break, since we had just now some kind of break. So I'm sorry if somebody just switched on. It will be not so easy to understand. But I mean, if you look at this part, it's okay, because I used only little bit of properties of upper bounds. In fact, the definition of upper bound is repeated here, so it's not so big deal if you lost the first part at the moment. So there is a claim that Xi, which exists by the completeness axiom, is indeed the supremum which we are seeking for. We look for the least upper bound, and we claim here it is. Okay. Let me recall. So you see that definitely what we need to check if is, first of all, Xi is an upper bound. Why? Look. Suppose not, by contradiction. By contradiction. So, if Xi is not an upper bound, what it means? Upper bound means that for all a in M, a less or equal than y. If it is not an upper bound, hence, then there exists a in M such that A satisfies opposite inequalities. So A greater than Xi. Then, in particular, A plus Xi over 2 is between them, so belongs to the interval A Xi. In particular, A plus Xi over 2 is less than A, so what we have? A plus Xi over 2 is greater than Xi. then by this implication of A12, A plus xi over 2 is in B. But B, what is B? The set B is the set of all upper bounds. So A plus xi over 2 is an upper bound. For M. But it cannot be upper bound of M. A plus xi over 2 less than A. And A is an M. So contradiction. Contradiction. So it means xi is indeed an upper bound. Is indeed an upper bound. And this is the least. So xi is the minimum upper bound. Why? Because if x less than xi, then by another implication of A12, x belongs to A, or it's the same as to say x does not belong to B. And this is x is not an upper bound. So you see, once we take any number which is less than xi, this number cannot be an upper bound. So xi is an upper bound, and no number less than xi is an upper bound. Hence, xi is indeed the minimum upper bound. That's all. So it means we proved that A12 implies A12 prime. Now, second half of this assertion about equivalency. A12 prime implies A12. Okay. Now, we start with suppositions of A12. So, suppose A, B are such that for all x in A, y in B, x less than y, and A together with B, union with B, is the whole set of the real numbers. So this is what we have to suppose according to proof A12. A12. Now what we need to prove, okay, here is written what is conclusion of A12. So look, we need to prove the existence of such a number xi. Such a number xi. But look, you see that by the supposition, this part means that every y in B is an upper bound for A. Hence, A is bounded above. A is bounded above, and it is non-empty. This is also what's supposed in A12. So, hence by A12 prime, there exists supremum. There exists supremum of our set A. And I claim this is precisely that number xi which we want to obtain by A12. So what we have to check, okay, let x less than xi. We need to prove that x should be in A, okay, by contradiction. So, by contradiction. Let x belongs to B. Because what is contradiction to x belongs to A and B together, they fill the whole real line. Hence, if we suppose x does not belong to A, then x belongs to B. But what means x belongs to B? Recall, B contains, look, so if x belongs to B, then what we deduced here, every element of B is an upper bound for A. Then x is an upper bound for A. And what we obtain then? We have an upper bound for A which is less than xi. But xi was supremum, so the least upper bound. That is a contradiction. Contradiction. Okay. So it means that we have proved the first half of the assertion. of A12. If x less than xi, then x belongs to A. The second half, let y greater than xi. But then what it means? Xi is an upper bound, and we proved before, once we have something which is greater than an upper bound, then y is an upper bound for A. So then if we an upper bound for A should be in B, right? Why? Why this is the case? Because if we would suppose if y belongs to A, so what it means, y is an upper bound and simultaneously belongs to A, then y would be equal to supremum A, because an upper bound which is an element of A is automatically the least upper bound, and that is contradiction to y, but y greater than xi, and that is a contradiction. So it means that the supposition y belongs to A cannot be fulfilled, and we have indeed the conclusion which we wanted to prove. Okay, so we have two equivalent possibilities for the completeness axiom. A12 and A12 prime. Of course, there is a dual assertion about the least, the greatest lower bound. So, but we don't need to prove it, since it is easy to understand that this is like a remark. So infimum of a set M is equal to minus supremum of the set minus x, where x is an M. So it means that it is easy to reformulate every assertion about the greatest lower bound if we have some assertion about the least upper bound. Okay, that is the first section for today's lecture. And not yet, I'm sorry, because there is a very useful proposition. So proposition, let me 2.1. So B is supremum of M if and only if, I'll use this abbreviation if, always in future, if and only if, first, for all x in M, x less or equal than B, and second, arbitrary for any epsilon greater than 0, this is Greek letter epsilon, there exists x in M such that B minus epsilon less than x. So, in fact, is almost nothing to prove because, okay, shortly let me show how to deduce it. So, suppose let B equals to supremum M. Then B is the least upper bound, hence it is an upper bound. And the first condition is just B is an upper bound. So first means B is an upper bound. So it's okay. And this is the least upper bound. So every x less than B is not an upper bound. And in fact, what we use here is just the possibility that every x less than B is not an upper bound. So if x less than B, then we may put x by definition as B minus epsilon, where epsilon is greater than 0. So then x is less than B, and this is what we wanted to show. So B minus epsilon is not an upper bound, and this means exactly that there exists x in M such that this inequality holds. And conversely, the first is that B is an upper bound, and the second means that every number which is less than B cannot be an upper bound, hence b is the least upper bound. So, and now it's a good time to illustrate it on the picture. So what is supremum of a set? So you have a set M, and what is supremum? Supremum is the least upper bound. So here it's like that. So you cannot move it to the left without having some cross point to the right. So you cannot move this bound to the left. For example, let's say M contains numbers of this form, so on, all numbers of the kind 1 over n, where n is natural. Then supremum M is 1, because this is the maximal element. This is obvious. But what is 1 belongs to M, but infimum of M is 0, which doesn't belong to M. And why this is like that? Because of the next section. So now this is not proved yet, but we'll prove it just now. So next section is Archimedean property. So the theorem here, theorem 2.21, the set of natural numbers n is not bounded above. Proof. Of contrary, suppose n is bounded above. This is non-empty, so by A12 prime there exists supremum. Let us denote it by xi. Let's say. Okay. Then it means that in particular for any hence, better to say hence, for any natural n, we have n less or equal than xi plus xi. In particular, n plus 1, which is also natural number, is also less or equal than xi. N plus 1 is also a natural number. So we have for every natural n, we have n less than or equal to xi minus 1. Since this is valid for any n, it means, so xi minus 1 is an upper bound for n. And that is contradiction to our definition of xi. Xi is the least upper bound. Contradiction. And now it's a good point to explain why infimum of our set M is indeed 0. So it follows from that theorem. So corollary. For any epsilon greater than 0, there exists natural n such that 1 over n is between 0 and epsilon. And the proof is almost immediate. So 1 over epsilon is not an upper bound for n, because no upper bounds for n at all. Since it is not an upper bound, hence there is n natural such that n is greater than 1 over epsilon. Such that, and once n is greater than 1 over epsilon, what we have, okay, by properties of inequalities, we have opposite inequality. Both here both numbers are positive. Hence we have 0 less than 1 over n less than epsilon, which is equal to 1 over epsilon. That's all. And you see, this corollary explains why infimum of our set M is indeed equals to 0. Why? Because if infimum, 0 is obviously a lower bound for M, because here all numbers are positive. But once we have a positive number epsilon, it cannot be lower bound because of the existence of such a natural. So there is an element of M which is less than epsilon. So epsilon cannot be a lower bound. So 0 is indeed the greatest lower bound. Okay, there is one more consequence of Archimedean property, and in fact there are some ways to write down axioms such that this property is taken as an axiom, and in fact there are very nice theories which are, it's called p-adic analysis, where you have all other, you accept all other properties of real numbers except for Archimedean property, and of course completeness axiom is not valid as well as it is given. So this is, by the way, this is another version of completeness axiom, but I'll not prove the equivalence anymore. Now this is just a theorem. So theorem 2, 2, 2. Now, so for any real numbers x, y, x less than y, there is a rational number R in Q. Q we used for rational numbers, such that x less than R less than y. So R is between two real numbers. Okay, proof. Firstly, suppose y minus x greater than 1. So this is an additional supposition. Then we may assert even more. There is a natural number n in n such that it is between So how to prove it? This is a claim, right? Okay. Claim. So how to prove this claim? So consider the set of all natural m such that m less than or equal to x. This is obviously a bounded set because x is an upper bound for this set of naturals. So let m, capital N is not good. Okay. M naught is supremum of this set. I'll use notations for. So this is precisely this set of all natural m such that m less or equal to x. So this is non-empty bounded above set, hence such supremum exists. Obviously, it should be in this set, right? Because if this is a natural number So if you have a set of natural numbers, then it either has no upper bound at all, or there are upper bounds in this set, hence there is a maximal element, in fact, right? So we have m naught less or equal than x as well. Then m naught plus 1 should be greater than x, because otherwise m naught plus 1 would be in the same set, and m naught could not be the least upper bound. So what we have then, I claim that this can be taken as n for our claim. So this is suitable to prove our claim. Why? Obviously n is greater than x, and look, so y is greater than x plus 1, right? And x plus 1 is greater or equal than m naught plus 1, and that is n. So y is greater than x plus 1 by supposition. X plus 1 is greater or equal than m naught plus 1 because of this inequality, and m naught plus 1 is precisely n. So it means that y is greater than n, and x is less than n as well. So the claim is proved. Now we go back to our general case. So we have x less than y. So for general case, y minus x is a positive number, hence by corollary before, there exists natural n such that 1 over n is less than y minus x. So we have ny minus nx greater than y, greater than 1, sorry. Ny minus nx greater than 1. So by our claim, by the claim, there is wait a minute, I have a mistake here. There is an integer n in z. Yeah. So here also all integers. I'm very sorry, of course, integers, because nowhere we supposed x is positive. M in z, yeah. Here we should consider integers, not naturals. But now here in natural. Here natural. So by the claim there is an integer m such that nx less than m less than ny. Now we divide this inequality by positive number n, and we obtain x less than m over n less than y. So we have a rational number, m is an integer, n is natural, which is between those two real numbers. Okay, the proof is completed and the lecture is completed as well. Thank you if somebody listened to me. Okay. Just a minute. Что пошло? Okay, I hope that people who asked me. Now, here you see there is a concrete set. This is not a set of the set of all integers. Here we are talking about a particular set of integers. The set of integers m such that m less or equal than given x. Easy. All integers such that m less or equal than x. That is not the set of all integers. Only integers which are less or equal than x. And this set is bounded above because of there is an upper bound. X is an upper bound. So there is a supremum. The supremum. The only one. Z doesn't have a supremum, of course. The set of integers has no supremum. Of course, here you are right. But for the set, this is not the set of all integers. This is the set of integers m such that m less or equal than x. Okay? Yeah, so.